1.2 is all about the properties of real numbers. Now you might be thinking, well, aren't all numbers real? Give us a couple chapters and we'll introduce you guys into some non-real numbers. But first, we're going to learn how to graph and order them, as well as identify their properties. First, we have our natural numbers, and these are the numbers that we count, like 1, 2, 3, etc. Then we have whole numbers, and whole numbers add in the value of 0. But then it also still includes 1, 2, 3, and so forth. Then we have our integers, and this introduces the idea of having negative whole numbers, like -2, -1, or any other negative. And it also still contains 0, 1, 2, and everything above it. Then we have our rational numbers, and these are like our fractions and decimals. For example, maybe we have -5/2. But it could also contain the same numbers we've had before, like -1, 0, 1, etc. And it could also include positive fractions and decimals, such as 0.6, or maybe 105/7. And those are just a few examples. So we can see as we work from the outside of our square into the center, they all have some values in common, and that is, they all contain the values that come from the types of real numbers before them. However, we do have a separate category, which is our irrational numbers, and these ones are our non-fractions, and they are non-repeating or terminating, meaning they end, decimals. Some examples of this would be like pi, or the square root of 3, or a decimal like 1.79246, and it just keeps going on forever. Remember from yesterday that we said that variables represent numbers, so we're going to classify variables as to what type of real number they would be. The Boston Marathon has many runners each year. What set of numbers does not contain the number of people who ran the race? Well, let's start by saying, what type of number would the number of people who ran the race be represented by? What kind of real number from that list above? People, we have to have at least one person to run the race, which means people would be considered a natural number. And we notice that our natural numbers are actually found in all of these categories of real numbers, except they're not found over in the irrational category. Therefore, our answer is irrational numbers because they do not contain any of our natural numbers like the other categories do. Next, we're going to classify the variable according to the set of real numbers that describes its value. The number n of equal slices of pizza and the portion p of pizza in one slice. Let's look at our first variable, which is the number n of equal slices of pizza. When we go to count slices of pizza, we have to have at least one if there's any pizza left. So that means n is going to be considered a natural number. Now, if we look at the variable p, which is the portion of pizza, and remember, portion is a fancy way of saying that we have fractions. We could also draw a visual of the scenario to help us identify what type of real number it would be. We would have a pizza, cut it up into some slices, and if we just said we had this portion right here, then there gives us a visual that we have fractions. And therefore, the variable p is going to be represented by our rational numbers. Now we can look at graphing and stating the type of real number. Here's something really important. Always simplify before classifying. For example, with the square root of 4, we know the square root of 4 is actually the same thing as 2. And 2 is one of our natural numbers. Then we can go ahead and put a point just on positive 2 on the number line. Next, we have -5/2, and that's the same thing as -2.5. So we see a negative, and we might think integer, but integers are not decimals or fractions. Therefore, we have to move up a category, and this is a rational number. And it's going to come halfway between -2 and -3 on our number line. Next, with the square root of 2, it's not a perfect square, so we don't know its exact value unless we plug it into our calculator. Then, when we do, we're going to get 1.4142, and it keeps going on forever. It doesn't repeat, and it doesn't stop, therefore it's an irrational number. And it's going to be almost halfway between the 1 and the 2 on the number line. Next, we're going to compare an irrational number, square root of 17, with a rational number, 3.8, and see which one's larger. Let's say we don't have a calculator. What we're going to do is we're going to try to figure out what perfect square is this square root close to. Well, the square root of 17 is really close to the square root of 16, which is 4. Since we took a number smaller than the square root of 17, we know that the square root of 17 actually has to be bigger than 4. Therefore, the square root of 17 is going to be greater than 3.8, since our estimated value of 4 is larger than 3.8. Go ahead and give that a try on the next one. What perfect square is the square root of 26 close to? The square root of 26 is just a little bit over 5. Therefore, it's going to be less than 6.25. Lastly, we have our properties of real numbers. The first one is the closure property, in which it says if we have any two real numbers, and we're going to represent those with the variables a plus b, then the answer is also a real number. If we use the same property but for multiplication, it says if we take any two real numbers and multiply them, then the answer is also a real number. Then we have the commutative property, and this property is all about the order in which our addition or multiplication occurs. Let's say that we do 1 plus 2, well that's the same thing as 2 plus 1. Or if we did 1 times 2, that's the same thing as 2 times 1. But the associative property, this is all about groups. And a way to remember this one is when you associate with people, you have a group of friends that you're with. For example, if we did 1 plus 2 in parentheses plus 3, well that's the same thing as if we did 1 plus 2 and 3 with the 2 and the 3 in the parentheses. Or with multiplication, we could do 1 times 2 times 3, and that's the same thing as 1 times 2 times 3, but the grouping has changed. With the identitive property, we have to do something so that what we start with is the same as what we end with. So the identity never changes. If we had 3 plus 0, well the answer is still 3. Or if we did 3 times 1, our answer's still 3 there as well. When we hear of inverse, we should think of the word opposite. If we had 4, the opposite of addition is subtraction, so we could add a negative 4 in order to get an answer of 0. With multiplication, the opposite is division. If we had the number 4, we could multiply it by 1/4, and that way our numerator and denominator cancel, and we're left with an answer of 1. So anytime we're using the inverse addition property, the answer is always 0. If we're using the inverse multiplication property, the answer always has to be 1. Then we have the distributive property, and we're going to use variables again here. Let's say we have a times b plus c. Well, distributive property says we're going to multiply that a into both parts of our parentheses, and we're going to end up with a times b plus a times c. Here are several examples that we can use to identify which property they illustrate. In the first example, we're going to notice that our two fractions are flipped. They're opposites of each other, and we're using multiplication. When we said opposites is what we call inverses. So this will be the inverse property of multiplication. And the next one, each side has the same numbers. If we look inside of these parentheses, we're going to notice that we have the same grouping. Therefore, it cannot be the associative property because the group stayed the same. But the order within the parentheses did change. So this is the commutative property, and specifically of multiplication. Also, side note here, maybe a way to remember this one is commutative kind of sounds a little bit like communism, and communism is all about order. Next one, we have a 3 outside of our parentheses, and then all of a sudden it's inside with both variables. Therefore, we have the distributive property. Go ahead and try the next 3 on your own. D is a commutative property because we've changed the order of our addition. E is the identity property of addition because we started with one number and we ended with the same one. And on F, it's the associative property of multiplication because we've changed the grouping of what is inside of our parentheses.